Hi, today I'm going to introduce our ECCV2022-Oral work, Modeling Mask Uncertainty in Hyperspectral Image Reconstruction. My presentation contains 4 parts, including background knowledge, motivation, method, and experiments. In this work, we mainly focus on the coded aperture snapshot spectral imaging system, or called CASI. It firstly utilizes an optical hardware mask to compress hyperspectral image signals into a 2D measurement, and then uses software algorithms to retrieve signals based on the measurement, conditioning on the particular mask used in the system. In general, if there are different cases, you have different physical masks. Previously, what we did was given a CASI, we train a deep network for that system and directly use it in the testing phase. If there are n different cases with n different masks, we need to repeat training and testing process for n times. This would be really tedious. As you can see in the table, for some models, it already takes nearly a week to train for once. And we just wondering, can we use a single network to handle multiple CASI systems? Here, we provide 2 intuitive solutions. The first one is we train single deep network using the data from multiple CASI systems, and we directly test it on k different CASI systems. We call this as a many-to-many case, that we use multiple masks for both training and testing. Of course, you can directly train a deep network using the data from single CASI and apply it to different CASIs during testing. This is called one-to-many setting, that training using single mask and testing using multiple masks. As summarized in this table, we call the same mask setting as well calibration. The other settings are called miscalibration because there's always a mismatch between the encoder and decoder in terms of the mask. As the line plot shown here, we test 4 popular deep networks under different scenarios. Each color demonstrates a scenario, and each column denoting a method. As you can see by the blue arrows, all other methods experience large performance descent if we want them to handle different CASI systems. The reason to this phenomenon is that the neural network is highly sensitive to the masks, and we can treat them as hyperparameters of the model. By comparison, what we did is to model the mask distribution. The observed mask histogram is shown by orange. We decompose the mask M into the binary mask M tilde and the Gaussian noise Z. We assume the binary mask follows the Bernoulli distribution, which is shown in blue, and the noise map D is sampled from a Gaussian distribution. We use green to represent it. We propose to use a standard variational inference treatment to solve the problem. For example, we don't directly compute the mask distribution Pm given xy, but assume a simpler distribution Q phi m parameterized by phi, and we minimize the KL difference between these 2 distributions. This learning objective could be divided into two terms. One is called the reconstruction term, and the other is called the regularization. For the regularization term, we assume Q phi m is a Gaussian distribution, where phi means the learnable parameters. For the reconstruction, we use L2 term by assuming a likelihood as Gaussian. Since we treat the mask as hyperparameter, it would be better to use a bilevel optimization procedure rather than a single level, considering a hyperparameter optimization of the mask distribution. We do extensive experiments to verify the proposed method. Our evaluation study shows that each module makes a contribution to the final performance boost. Here, we provide a metric comparison between different methods under the miscalibration scenario many-to-many, where all the methods are trained by a mask dataset M and tested by random masks. By comparison, we achieve around 0.8 dB performance improvement over the previous best method. At last, we visualize the uncertainty modeling. The observed mask distribution is shown in blue, while our learned mask distribution is shown in orange. In the bottom line, we visualize the variance map, or to say the uncertainty map of different methods. The darker it is, the better uncertainty estimation, the more confident the network is, and thus more reliable. Thanks for listening. In the link below, we open source our training and testing code of this project. For more empirical evidence and details, please refer to our paper. If you have any questions, feel free to contact me.